Okay, we are looking at section 5.3. The beginning part of it's going to be a little bit of a challenge. Ends easier than it starts. In this section, we're going to be finding the equation of a tangent line. Again, that's the easy part. And in the process, we're going to be finding definitions for the differentials dy and dx. Now, where you've seen dy and dx, I don't write it very often because it's a longer way to do it, is when we do derivative. We always called it y prime. Y prime equals, well, remember the other notation for that is dy over dx. And we think of that as one unit, but in this lesson, we're going to be separating the two and finding definitions for each one individually. So it all starts with a nice complicated graph. So say we have a function. There's our original function, which we'll call f of x. We'll pick a point, and we'll do the tangent line business. So that linear function we'll call a y. And it's of the form y equals mx plus b. And because that's a tangent line, first of all, let's go down here. It's all about the labeling. So at some given x value, which I'm going to call a, they have the exact same y value. So f of a and y of a are exactly the same value. I've got y of a equals f of a there. The tangent line and the function, that's the only point they have in common, so they share that y value. What we're going to do is move away from x, a small amount, but I'm going to exaggerate it, to x plus some change in x, like a 0.01 away, or a 0.001 away, or maybe a 0.1 away. So we're going to call that x plus delta x, or I should say the book calls it x plus delta x. I'm just going to call it b. It's going to make life a little bit easier. Now what happens when we move away from that point they have in common, they no longer have the same y value. I'm going to stretch this out here. Dang, you probably ran into yours too. This new y value on the tangent function we'll call y of b, because I've got that equation called y equals. So that's y of b. The corresponding y value, I'm going to bend it a little bit so it hits. We'll call that one f of b. Because I chose to call the original function f of x, so that's the y value at b, so f of b. The linear function I've defined as y equals, so I can distinguish between the two functions, f of x and y. Well, let's get rid of that. Okay, all of our definitions are going to come out of this. Okay, this change in x, when I went from a to b, or x to x plus delta x, that change there, well, obviously it's called delta x. And delta x is the change in x on the original function. So delta x is the change in x on the original function. Well, it's the same change in x on the tangent function. So delta x is equal to dx. They're the same value on both functions. Now the y's are different. Delta y is the change in y values on the original function. So these are just definitions, the way it works. So it's the f of b value, the new one, minus the original one. So it's this big jump. It's this distance. Deltas are changing. So it's the change in y value on the original function. So it's f of b minus f of a. Now dy is the change in y values on the tangent line. So that's y of b minus y of a. Okay, and this is the one that's kind of important. There's another way to get this answer without doing a tangent line. And its definition is f prime of x times dx. So both of these yield the same answer, and it's the change in y value on the tangent line, or for the tangent line. I should have told you this one too. This one's the change in y value on the original function. So change in y on original function. Okay, if you can read that, change in y on the original function. Sorry about that. And this is just the change in x on both. Okay, now at the original point where there is no change in the y values between the two y values, here there is a difference in the two y values. That's called the error of the function. So error is the distance between these y values here at the second point, the second x value. So the error would be calculated by taking the y value of the original function and subtracting the y value of the tangent line function. So this is your error right in here, that distance. Okay, these are the definitions you need to do this next problem. Let's see. I think I want to start a new page just in case it takes a little more. All right, so 4 f of x equals 11 minus x cubed. Find an equation of the, I'm going to phrase this just like the book does. Find an equation of the linear function that best fits at x equals 2. Okay, what are they asking you to do there? All they're asking is find the equation of the tangent line at 2. Why they got to be so complicated? I have no idea. So this is just the tangent line at x equals 2. Once you do that, I want you to be able to identify delta x, dx, dy, delta y, and the error at x equals, I'm going to go 1.9. Okay, here we go. Sketch would be nice so you can keep track and kind of tie it into what we just did. So I'll quickly sketch. I might even have it in here still. I do. 11 minus x cubed. I know that it's hitting up at 11, but window, I can increase that max to like 15. Oh, wrong max. Y max. 15. I can get rid of some of this. 5. So 11. I only care about at 2. I can see it's crossing just past the 2. So I'm going to exaggerate this a little bit. So at 2, I want to find the equation of the tangent line, and then find all of this information, these 5 things, at 1.9. So just a rough sketch of the tangent line in here. Oops, I'm supposed to hit. I'm going to call 1.9 way down here just so I can get some separation. Because you know at the tangent spot there's only one y value. We're going to need to know that. Because that's my a. This is my b, or my x, and then my x plus delta x. So my original value was the original x value. I called it a. 1.9 is my new new x value, which I call b, and then the book will call that x plus some delta x, which we can see was just a negative 0.1. But anyway, at this point, you know the graphs are separated, so you have 2 separate y values here, which we'll find later. So we're going to be having 3 functions working here. The original function, 11 minus x cubed. We're going to be using the tangent function, excuse me, not tangent, but derivative function. So let's write that one down right now. The derivative function, derivative of 11 is 0. Here we get negative 3x squared. And then we still have to come up with the tangent line, y equals. So I'll leave room for that one up here. So tangent line first, we'll call it part A of the problem. Tangent line. Your first step is to always find the slope. And you know the slope. At this point, you should remember, we've done this quite a few times, that the slope comes from the derivative. So we want the slope when x equals 2. When x is 2, we want the slope. So the m is the derivative value at 2. So if I plug 2 into the derivative, I get negative 3 times 2 squared. Let's see, it's negative 12. Now the second step is to find the b. And just by my graph, I can see it's going to cross up pretty high. This was at 11, so I'll go into the y equals mx plus b. I can substitute in for the m. I know that that's negative 12. The x I know is a 2. I'm supposed to be able to solve for the b. I don't have a y. Well, where do I get the y value from? Well, think about it. If x is 2, there's a y value here. I just never found it. How can I find this y value? Well, this y value is on the original function. I've just got to put 2 into the original function to see what the corresponding y value is. So the f of 2, 2 cubed is 8, 11 minus 8 is 3. This is 3. So that's my f of 2 value, or my f of a value, and my y of a value. So I can put a 3 here. This will be negative 24, so I'm going to add 24 to both sides. So b equals